There is a telescope sitting in space right now that can see the light from galaxies that formed just a few 100 million years after the Big Bang. It can peer through clouds of dust that have hidden stellar nurseries from human eyes for the entire history of our civilization. It has rewritten what we thought we knew about the early universe, about exoplanet atmospheres, about the formation of stars, about the very structure of existence itself. And the story of how it got there is one of the most dramatic, complicated, and frankly unbelievable engineering sagas in the history of science. Because here is the thing that most people glossed over when the James Webb Space Telescope launched on Christmas Day in 2021. That telescope had technically been finished for years. It sat in a warehouse, wrapped up, waiting, for 4 years, while engineers and scientists and project managers argued about whether it was actually safe to send into space. If you want to understand what was really going on during those 4 years, and why the final decision to launch was so complicated, and what actually changed in the final risk assessment that gave everyone enough confidence to strap it to a rocket, then stick around. Because this story goes much deeper than a delayed launch, this is a story about what it actually takes to trust a machine you can never, ever touch again. And if you haven't subscribed yet, do that now, because this is exactly the kind of story we tell here, and there are a lot more where this came from. Let's start at the beginning, not the launch, the actual beginning. The idea for the James Webb Space Telescope was born in the late 1980s. Hubble hadn't even launched yet. Scientists were already sitting in rooms dreaming about what came next. They knew Hubble was going to be transformative. They also knew it had limits. Hubble was designed primarily to observe invisible light and ultraviolet wavelengths. The universe has a lot more to say in infrared. To see the oldest, most distant light in the universe, the light from the first galaxies that ever formed, you need infrared sensitivity. You need a telescope that can detect the heat signatures of objects that are so far away that the expansion of the universe itself has stretched their light out of the visible spectrum entirely. That process is called redshift, and it is the key to understanding everything that Webb was designed to do. So in 1989, a group of astronomers got together for what became known as the Hubble Space Telescope and Beyond Workshop. They were thinking about what a next-generation telescope might look like. The ideas that came out of that meeting were ambitious, extraordinarily ambitious. They were talking about a mirror several times larger than Hubble's, positioned not in low Earth orbit where Hubble lives, but somewhere much further out. A place called the Second Lagrange Point, or L2, which sits about 1.5 million kilometers from Earth in the direction directly away from the Sun. At L2, the gravitational forces of the Sun and Earth balance out in a way that allows a spacecraft to essentially hover in a stable position relative to our planet while orbiting the Sun. This is perfect for an infrared telescope because you can position the sun shield between the telescope and the Sun, Earth, and Moon simultaneously, blocking all of that heat and light and allowing the instruments to cool down to the extraordinarily low temperatures required for sensitive infrared detection. The first formal recommendations for what would become Webb came from a 1996 report called the HST and Beyond Committee. At that point, the telescope was being called the Next Generation Space Telescope, or NGEST. The target launch date back then was 2007. The estimated budget was around $500 million. If you know anything about how this project actually went, you are probably already laughing. NASA formally selected the design concept in 1997 and began partnering with the European Space Agency and the Canadian Space Agency to share the enormous workload. The name was changed to the James Webb Space Telescope in 2002, honoring NASA Administrator James Webb, who had overseen the agency during the critical years of the Apollo program. And then the real work began. Here is what made Webb so uniquely difficult to build. Everything about the scientific requirements pushed against the physical realities of launch. You need an enormous mirror to collect enough light to see those first ancient galaxies. The primary mirror ended up being 6.5 meters in diameter, which is roughly the size of a 2-story building. Hubble's mirror is 2.4 meters. That difference is massive in terms of light collecting area, but no rocket on Earth can fit a mirror that large in its payload fairing in a single rigid piece. So the engineers designed the mirror to fold, like origami. 18 individual hexagonal segments made of beryllium, coated in a microscopically thin layer of gold that would lock together into their final configuration only after the telescope had already been launched into space. And that was just the mirror. The sun shield, the thing responsible for keeping the telescope cold enough to function, had to be even more improbably engineered. 5 layers of a material called kapton, each layer thinner than a human hair, stretched across an area the size of a tennis court. The sun shield had to fold up into a package that could fit inside the Ariane 5 rocket, and then unfold precisely and completely in the vacuum of space after launch, with no human hands to guide it, no astronauts to fix it if something went wrong, no second chances. That last part is the thing that haunts this entire story. Webb was going to L2. That is 1.5 million kilometers away. The furthest humans have ever been from Earth is about 400,000 kilometers, which is roughly the distance to the Moon. No human spacecraft has ever traveled to L2 with a crew. No human ever could go out and service Webb the way astronauts serviced Hubble on 5 separate servicing missions between 1993 and 2009. Webb was entirely on its own from the moment of launch. This meant that everything had to work. Every single deployment, every mirror segment alignment, every instrument activation, every thermal control mechanism. All of it perfectly, the first time, with no possibility of repair. And there were 344 single-point failures in the deployment sequence alone. A single-point failure is an engineering term for a component or mechanism that, if it fails, causes the entire mission to fail. Not just degrades it, ends it, completely. 344 of them, spread across the most complex deployment sequence ever attempted on an unmanned spacecraft. The number 344 became almost mythological during the development of Webb. Engineers talked about it. Journalists wrote about it. It was the number that kept everyone awake at night. And it was the number that sat at the center of the final risk debate that kept the telescope on the ground for 4 additional years after it was, at least in some technical sense, ready to fly. Now let us get into what actually happened during those years in storage, because this is where the story gets truly fascinating. Webb was declared technically complete in 2017. The telescope and its instruments had been assembled, tested in simulated space conditions, and signed off on by the engineering teams. It was moved to Northrop Grumman's facility in Redondo Beach, California, where it would undergo final integration and then wait for launch. The original launch date at that point was October 2018. Then it slipped. Then it slipped again. Then again. Eventually it became April 2019, then March 2020, then March 2021, and finally December 2021. Every slip generated headlines. The press had a field day. Webb was called the telescope that ate NASA's budget, which was not entirely unfair given that the project had grown from that original $500 million estimate to a final cost of approximately $10 billion. Congressional hearings were held. There were genuine discussions about whether to cancel the mission entirely. A 2011 report from the House Appropriations Committee's Commerce, Justice, and Science Subcommittee actually voted to terminate Webb's funding entirely. The project survived, but only after significant restructuring, a new management team, and a congressional cap of $8 billion that was eventually exceeded anyway. But here is the thing that did not get reported as clearly during those years of delays. Not all of those delays were just about incompetence or mismanagement or bureaucratic inertia. Some of those delays, particularly the final stretch of them, were about something much more fundamental. They were about the question of whether the risk profile of the mission had been honestly and completely characterized, and whether anything could be done to improve it. In early 2018, something happened that clarified the problem in a very stark way. During testing at Northrop Grumman, engineers discovered that the vibration transducers used to monitor the spacecraft during acoustic testing had been providing incorrect data. The acoustic tests subject a spacecraft to the intense sound pressure of a rocket launch to verify that nothing shakes loose or fails under those conditions. If the monitoring equipment is not calibrated correctly, you might think you have good data when you actually have bad data. When this was discovered, a review was ordered. And the review found other issues. Fasteners. Specifically, a set of screws securing the sunshield cover had vibrated loose during testing. Not catastrophic on its own, but deeply concerning. If screws were vibrating loose during a simulated launch on the ground, what might happen during the actual launch? The incident triggered a top-to-bottom review of the testing program and the telescope's readiness. And this is where the 4 years in storage become less about a passive waiting period and more about an active, sometimes agonizing reassessment of what was known versus what was assumed. One of the central tensions in aerospace engineering is the difference between testing and analysis. Ideally, you test everything. You simulate every condition the spacecraft will face, and you verify that every system responds correctly. But there are limits to what you can test on the ground. You cannot fully replicate the vacuum of space. You cannot fully replicate the temperature gradients that a spacecraft experiences as it transitions from the warmth of Earth's environment to the extraordinary cold of deep space. You cannot fully replicate zero gravity. So engineers use analysis, meaning mathematical models and computer simulations, to fill in the gaps between what testing can verify and what the spacecraft will actually experience. The problem is that analysis rests on assumptions, and assumptions can be wrong. And if the assumptions are wrong, the analysis is wrong. And if the analysis is wrong, you might believe you have verified something that you have not actually verified. During the extended review period after the 2018 incidents, the teams went back through the assumption chain on many of Webb's critical systems. They were asking a very specific question. Where have we relied on analysis to cover gaps in testing, and how confident are we really in that analysis? Some of what they found was reassuring. The analysis was solid, the models were well calibrated, and the risk was genuinely as low as the numbers said it was. But in some areas, they found that the confidence intervals were wider than they had acknowledged. Not that things were going to fail necessarily, but that the uncertainty was higher than the official risk numbers reflected. And in mission-critical systems with no possibility of repair, high uncertainty is itself a problem, regardless of what the central estimate of the probability says. This is a subtle but enormously important distinction. Think of it this way. If someone tells you there is a 1% chance that a bridge will collapse while you are crossing it, you would probably not cross it. But if someone tells you there is a 1% chance, but also admits they derived that number by assuming certain things about the bridge's construction that they never actually verified, then your confidence in that 1% figure should be much lower. The stated probability might even be accurate, but the foundation it rests on is shakier than the number implies, and that matters. The teams working on Webb spent those years in storage, doing something that sounds almost paradoxical. They were trying to verify the verification, going back through every signed-off test result and every approved analysis and asking whether the confidence that had been assigned to those results was actually justified. This is not a normal part of spacecraft development because it is expensive and time-consuming, and it implies that your previous work might have been inadequate in some way. It takes a particular kind of institutional honesty to do it, and it was genuinely hard. One area that received sustained attention was the deployment of the sunshield. The sunshield is arguably the single most critical non-propulsive system on the entire spacecraft. If it does not deploy correctly, the telescope's instruments never cool to their operating temperatures, and the mission fails completely. The sunshield deployment sequence involves hundreds of individual mechanisms: pins that release, cables that retract, membranes that unfurl, tensioning systems that pull each layer taut. Every one of those mechanisms had been tested individually. The question that became increasingly pressing was whether the behavior of the whole system, when all of those mechanisms fired in sequence in the actual thermal and vacuum environment of space, could be confidently predicted from the sum of those individual tests. The answer, after extensive review, was mostly yes, but with some important caveats that needed to be addressed. One of the specific issues that emerged involved what engineers call margin. In engineering, margin is extra capacity built into a system beyond what it theoretically needs to function. If a cable needs to support 100 pounds of tension, you might design it to support 200 pounds, giving yourself a factor of 2 margin. Margin is your buffer against uncertainty. And during the deep review of the Sunshield deployment system, engineers found that the margin on certain mechanical elements of the deployment was smaller than they would have liked, particularly when they accounted for the fact that the system had never been tested as a complete integrated unit in actual space conditions. There is a reason it had never been tested as a complete integrated unit in space conditions. You cannot. The Sunshield, when fully deployed, is the size of a tennis court. There is no facility on Earth capable of putting it in vacuum and deploying it at full scale in simulated zero gravity at the correct temperatures. This is simply a physical limitation of ground-based testing. No matter how much money you spend or how long you wait, you cannot build that test. The only way to know for certain that the Sunshield deploys correctly in space is to deploy it in space. This reality forced the teams into a different kind of work. Rather than trying to directly test their way to confidence, they had to build it analytically. They improved the fidelity of their computer models. They did more component-level testing to better characterize the behavior of individual mechanisms under representative thermal conditions. They traced through the deployment sequence step by step and identified which mechanisms were most critical and which failure modes were most plausible. And then they did something very important. They made changes to reduce those risks wherever they could. One of the most significant changes involved the way the deployment sequence was structured. Engineers developed a more conservative sequencing approach for several critical deployments, adding additional monitoring checkpoints and building in more time for temperatures to stabilize at each stage before proceeding to the next step. This meant that if something looked anomalous partway through a deployment, there would be time to assess it before committing to an irreversible next step. They also made changes to certain mechanical components. Some hardware was redesigned to provide better margin. In some cases, this required requalification testing of the new designs, which added time. But every change that improved the margin, even marginally, on a critical deployment mechanism was considered worth the additional schedule impact. Because the alternative was launching with known concerns about margin adequacy, and with Webb, you could not go back and fix it later. There is another dimension of this story that is easy to overlook, and it is purely human. The teams working on Webb had been working on Webb for a very long time. Some engineers had spent their entire careers on this single project. The culture around a program that long and that expensive develops its own momentum, its own assumptions, its own ways of seeing things. There is a kind of group knowledge that builds up over years of working on a system, and that group knowledge is genuinely valuable. But it can also create blind spots. Things that everyone in the room has always assumed can stop being examined with fresh eyes simply because they have been assumed for so long. NASA brought in outside reviewers, independent teams who had not spent years inside the Webb program, to conduct assessments of the risk posture. These independent review boards had a license to ask the basic questions that internal teams might have stopped asking. Why do we believe this will work? What would it look like if it did not work? What are we assuming, and have we tested those assumptions? The findings from these reviews were not uniformly alarming. In many cases, they confirmed that the risks were well characterized and the mitigations were appropriate. But they also surfaced specific concerns that led to additional testing and analysis work. And in some cases, they led to changes in how risks were officially categorized and communicated, which matters because the official risk categorization determines how much attention and resources a concern receives. One of the deeper shifts that happened during those 4 years was a change in how the program talked about risk publicly and internally. In the earlier phases of the program, there had been a tendency, common to many NASA programs under budget pressure, to present risk estimates in their most optimistic, plausible form. This is not dishonesty exactly, but it is a kind of selective emphasis that can compound over time. When optimistic estimates become the baseline for planning and communication, any honest accounting of uncertainty starts to look like pessimism or obstruction, and people who raise concerns can find themselves marginalized, which creates a feedback loop that pushes the program further toward overconfidence. What happened in the final years of Webb's pre-launch development was, in part, a cultural correction. The program moved toward a more rigorous accounting of uncertainty. Risk estimates were required to include explicit acknowledgement of the assumptions they rested on and the degree to which those assumptions had been tested. This made the official risk numbers look worse in some cases, not because the actual risks had gotten worse, but because they were being characterized more honestly. And paradoxically, this made the launch decision ultimately more defensible, not less, because it meant that when engineers said the risk was acceptable, they were saying it having done the hard work of actually understanding what the risk was. Let us talk about what the final risk assessment actually said, because this is the part of the story that often gets lost in the broad narrative of delays and cost overruns and eventual triumph. The ultimate question that any launch decision reduces to is this: given everything we know, is the probability of mission success high enough to justify proceeding? For Webb, mission success was defined in tiers. There was a minimum success scenario, in which Webb would still return scientifically valuable data, even if not all systems performed optimally. There was a full success scenario, in which all systems performed as designed. And there was the failure scenario, in which one or more critical systems failed in a way that ended the mission. The final pre-launch risk assessment concluded that the probability of achieving at least minimum mission success was very high. The specific numbers involved in official NASA risk assessments are typically not made public in complete detail, but the confidence level expressed by senior engineers and mission leadership in the months before launch was genuine, and it rested on a foundation of completed work that the earlier, more optimistic projections had not fully earned. Critically, the 344 single-point failures had not gone away. You cannot design them away completely in a mission of this complexity. What had changed was the confidence in the characterization of each one. The teams had gone through every one of those 344 points and asked, do we understand this mechanism? Do we have high confidence that it will function correctly? If it fails, do we understand what the failure mode looks like, and is there anything we can do to detect it early enough to matter? In most cases, the answer to all of those questions, after the extended review and remediation work, was yes. In some cases, the honest answer was that there was nothing more that could be done to reduce the risk short of a fundamental redesign that was not feasible. In those cases, the decision came down to whether the risk was acceptable given the mission's value, and the judgment was that it was. This is how these decisions always ultimately work. At some point, you have done everything you can do within the constraints of physics and budget and time, and then someone has to make a call. But the call is much sounder when it is made after genuine exhaustive work than when it is made after optimistic hand-waving. There is one more element of the launch preparation story that deserves careful attention, and it involves the rocket itself. Webb launched on an Ariane 5, a European rocket operated by Arianespace. This was not a trivial choice. The decision to use Ariane 5 had implications for the risk assessment in both directions. On the positive side, Ariane 5 had an extraordinary reliability record. By the time Webb launched, the rocket had completed 111 consecutive successful launches. That is an almost unheard-of reliability record for an orbital launch vehicle. The rocket was well understood, well characterized, and the teams who operated it had enormous experience managing its behavior across a wide range of payload configurations. On the more complex side, Webb's configuration on Ariane 5 was unusual. The telescope was an extremely large payload, and it was packed in a very specific way that affected the acoustic and vibration environment during launch. Remember that the fairing, the nose cone that protects the payload, creates an acoustic cavity during launch as the rocket's engines fire and the vehicle pushes through the atmosphere. The sound pressure inside that cavity is enormous, and for a payload as large and structurally complex as Webb, the coupling between the acoustic environment and the structure was something that required very careful analysis and testing. The 2018 incident with the vibrating screws had actually led to additional acoustic testing work that improved the understanding of how Webb responded to the launch acoustic environment. The updated testing, combined with Arianespace's cooperation in refining some parameters of the launch profile to moderate the acoustic environment where possible, gave the teams better calibrated expectations for what Webb would experience during ascent. There was also a very specific concern about the moment of payload fairing separation. When the fairing separates, the pressure environment around the spacecraft changes suddenly and dramatically. For a structure as delicate as Webb's folded sunshield, there was a carefully analyzed risk that this pressure transient could cause unexpected behavior. The teams had modeled this extensively and were confident in the analysis, but it was one of those gaps where you are relying on analysis to cover territory that testing cannot fully reach. The launch on December 25, 2021 went beautifully. The Ariane 5 performed flawlessly. The fairing separated cleanly. Webb was deployed from the upper stage without incident. And then the deployment sequence began, the one that engineers had spent those 4 years reassessing and refining and worrying about. The first major deployment milestone was the solar array. About 29 minutes after launch, Webb's solar array unfurled and began generating power. This was the first irreversible step, and it worked perfectly. Then came the high-gain antenna. Then, over the following days, came the secondary mirror deployment and the primary mirror wing deployments. And through it all, the most watched piece of deployment hardware in the history of science, the sunshield. The sunshield deployment took several days and was broken down into numerous individual steps. Each one was monitored by the mission operations team in real time. Each one worked. The 5 membrane layers unfurled. The tensioning system pulled each one taut. The full tennis court-sized thermal barrier took its shape in the darkness of space, 1.5 million kilometers from the world that built it. Watching the operations team in those days was like watching people exhale after holding their breath for years. Because in a real sense, some of those engineers had been holding their breath for years. The work of those 4 years in storage, the reviews and the remediation and the retesting, and the honest reckonings with uncertainty, all of it had been pointing toward this moment. And the moment came, and it worked. But let us not leave the story there, because the launch and deployment was not the end of the risk story. It was, in some ways, the beginning of a new phase of it. After deployment, Webb entered a roughly 6-month commissioning period. During this time, the instruments were powered on for the first time in their actual operating environment. The mirror segments were aligned, and the telescope was calibrated. This phase had its own risks, some of which were anticipated and some of which were not. The mirror alignment process was something that had been designed with great care and a lot of built-in margin for iteration. The 18 hexagonal primary mirror segments each had 6 actuators behind them, tiny motorized screws that could adjust the position and orientation of the segment to within nanometers. The alignment process involved taking images of a single star with the full mirror and using the resulting pattern of light to determine the precise misalignment of each segment, then commanding the actuators to correct for those misalignments, and repeating this cycle until all 18 segments were behaving as a single coherent mirror. This process worked better than expected. The final alignment achieved an image quality that exceeded pre-launch requirements. One of the things that genuinely surprised the team in a positive way during commissioning was the performance of the telescope's propulsion system. Webb uses thrusters for station keeping at L2 and for attitude control. The Ariane 5 launch had been so precise, placing Webb on such an accurate trajectory, that the spacecraft used significantly less propellant than expected for the mid-course corrections needed to reach its final orbit at L2. The margin of propellant that this freed up has extended Webb's expected operational lifetime. The original design life was 10 years. The precision of the launch and the resulting propellant savings means that Webb now has enough propellant to potentially operate for 20 years or more. This is not a small thing. It means that the scientific return from Webb could be roughly double what was originally planned. This outcome points to something that the extended pre-launch period contributed to, even if indirectly. The obsessive attention to understanding and characterizing every system, the culture of honest accounting of what was known and what was assumed, extended beyond the telescope itself to the whole mission architecture. The launch team's focus on trajectory precision was part of that same culture. Get it right. Understand the uncertainties. Do not assume that good enough is close enough. Now let us pull back and think about what this story actually means, because there is something here that goes beyond the specifics of Webb, and that is genuinely worth sitting with. The history of space exploration is, in part, a history of risk. Every mission involves accepting risks that cannot be fully eliminated. The question is never whether risk exists. It is whether the risk is understood and whether it has been honestly assessed. And the history of space exploration is also, honestly, a history of what happens when risks are not honestly assessed. The Challenger disaster in 1986 happened because concerns about the O-ring seals on the solid rocket boosters had been raised, had been documented, and had ultimately been overridden by schedule pressure and by a culture that had normalized the fact that the seals were operating outside their qualified temperature range. The engineers knew there was a problem. The culture made it too hard for that knowledge to translate into action. The Columbia disaster in 2003 happened because foam strikes on the orbiter's thermal protection system had happened before, had been observed before, and had been assessed as acceptable risks in a way that turned out to be catastrophically wrong. Again, there was a culture problem. There was a normalization of a known hazard that should never have been normalized. Webb was not going to kill astronauts if it failed. The human cost of failure would be measured in lost science and in the enormous investment of treasure and labor that the telescope represented. But the institutional lessons of Challenger and Columbia were very much present in the room during those 4 years of pre-launch review. The question of whether risks were being honestly characterized versus optimistically smoothed over was explicitly part of the conversation. The independent review boards that were brought in to assess Webb's readiness were operating in direct response to the institutional failures that those disasters had revealed. This is one of the things that the 4 years in storage actually accomplished. It created space for the kind of institutional honesty that is very hard to maintain when you are moving fast. When you are under pressure to meet a schedule and stay within a budget and deliver results, the temptation to round down the uncertainty and round up the confidence is enormous. Not because people are dishonest, but because everyone is trying to get the job done, and the job feels achievable, and the concerns feel manageable, and you just keep going. The 4 years in storage interrupted that momentum. They forced the program to stop and take stock. And taking stock honestly revealed things that needed to be addressed. Does this mean the 4 years were worth it? In the narrow sense of whether those specific delays were all strictly necessary, the answer is complicated. Some of the delays were caused by genuine technical problems that needed to be solved. Some were caused by human error in testing. Some were caused by the legitimate but time-consuming process of doing more thorough reviews. And some, honestly, were caused by the institutional dysfunction of a program that had grown too large and too complicated for its original management structure to handle well. Not all of it was noble. Not all of it was efficient. But in the broader sense of what those years produced, the answer is clearer. Webb launched with a more thoroughly characterized risk profile than it would have had if it had launched in 2018. The teams that launched it had a more complete and more honest understanding of what they were putting in the air. And that understanding showed up in ways large and small during the deployment and commissioning phase, in the careful sequencing of deployments, in the calibrated expectations for how systems would behave, in the ability to recognize nominal behavior when they saw it because they had done the work to know what nominal looked like. There is a version of this story that treats the 4-year delay as pure failure, overruns, mismanagement, a telescope that sat in a warehouse while the scientists who had designed experiments for it grew older and waited. And there is truth in that version. The delays were real. The cost growth was real. The frustration was real. But there is another version. A version in which a program that had developed some of the same cultural blind spots that afflicted NASA before its greatest tragedies stopped, examined itself honestly, did the hard work of filling in the gaps between what was known and what was assumed, and ultimately launched one of the most complex machines ever built, with a level of genuine confidence that the earlier schedule would not have earned. Both versions are true. The question of which one you emphasize probably says something about what you think the most important lesson is. What is not debatable is the result. Webb is out there right now. It is operating. It has been operating since 2022, and everything about its performance has met or exceeded pre-launch expectations. The images it has returned, from the stunning deep field image released in July 2022 showing galaxies that formed just hundreds of millions of years after the Big Bang, to the spectroscopic data on exoplanet atmospheres, revealing the chemical signatures of worlds orbiting distant stars, to the stunning detail in stellar nurseries like the Carina Nebula that showed structure invisible to previous telescopes, have delivered on the extraordinary promises that justified the extraordinary cost and the extraordinary patience required to build and launch it. The science is extraordinary, but so is the engineering story behind it. And one of the things that makes the engineering story worth telling is precisely that it was not clean. It was not a triumphant march from design to launch. It was a grinding, sometimes painful, occasionally humiliating process of building something at the absolute edge of what human ingenuity could achieve, and then having the discipline to stop before launch and ask, honestly, whether you had actually done it right. Think about what it takes to sit with a finished machine for 4 years and keep asking that question. The telescope is done. The science is waiting. The scientists who spent their careers designing instruments for it are waiting. The budget is gone. Congress is asking questions. The press is writing unflattering stories. And you keep asking, are we sure? What are we assuming? What haven't we tested? What do we wish we knew that we don't know? That is hard. Not technically hard in the way that building the mirror was hard. Hard in a human way. Hard in the way that requires resisting pressure and resisting your own desire to believe that you have already done the work and it is time to go. The engineers and managers who did that work, who sustained that discipline through 4 years of delays and criticism and uncertainty, deserve to share in the credit for what Webb has become. The telescope works because of the physics and the engineering and the materials science and the optics and the software, but it also works, perhaps, because some people in some conference rooms insisted on asking the hard questions for long enough to get answers they could actually trust. And one more thing about those 4 years that is easy to miss in the narrative of what was wrong and what needed fixing. Some of those years were not about fixing problems at all. They were about accumulating evidence that things were right. When you are dealing with systems that have never been tested in their actual operating environment, one of the most important things you can do is find every possible way to build confidence in your analysis through independent verification, testing something a different way and getting the same answer, running the simulation with a different team using a different code and getting consistent results, having engineers who were not involved in the original design walk through the logic and confirm that it holds up. This is not glamorous work. It does not generate headlines. It does not advance the hardware toward the launch pad in any obvious way. But it is the work that converts a stated confidence interval into an earned one. And for a mission of Webb's nature, with no possibility of repair, converting stated confidence into earned confidence was worth a very great deal. There is a moment in the Webb commissioning story that captures something essential about all of this. In February 2022, about 7 weeks after launch, the team released the first engineering image from Webb. It was not a science image. It was a mosaic of 18 blurry dots of light, each one representing the same star as seen by one of the 18 primary mirror segments, which at that point had not yet been aligned with each other. Each segment was functioning independently, pointing in a slightly different direction, producing its own separate image of the same star. The 18 dots were scattered across the field of view. It was not a beautiful image in the conventional sense, but to the people who had spent years working on this telescope, it was extraordinary, because those 18 dots meant that all 18 mirror segments were functioning. All 18 actuator systems were responding to commands. All 18 detectors were registering light. The science instruments were alive and functional. The sun shield was working and the telescope was cold. Everything that could be verified at that stage of commissioning was verifying correctly. And then, over the following weeks, the team began the long, careful process of aligning those 18 segments into a single coherent mirror. They adjusted the actuators one by one, measuring the improvement in image sharpness, iterating, refining. Each week the images improved. The 18 dots became 18 images of the same star overlapping each other. Then they began to coalesce. Then they merged into a single point of light that was sharper and more precise than any ground-based telescope could ever achieve. because ground-based telescopes have to look through a moving, turbulent atmosphere that blurs every image no matter how good the optics are. By early March 2022, Webb was producing a single sharp image of a star, and in the background of that engineering image, barely visible because the exposure was not optimized for them, were galaxies, thousands of galaxies. In what was intended as a simple calibration image of a single nearby star, Webb had captured thousands of galaxies in the background, each one containing hundreds of billions of stars, many of them billions of light-years away, and they were sharp, stunningly, impossibly, beautifully sharp. That image circulated through the astronomy community like electricity. This was not a released science image, it was a calibration frame, and it was already showing that Webb was performing at a level that the most optimistic pre-launch projections had only dared to suggest was possible. When the first official science images were released in July 2022, they stopped conversations around the world. People who had never cared about astronomy were sharing them on social media. The deep field image, the one showing galaxy clusters and gravitational lensing, and the ancient light of some of the first galaxies in the universe, was published on the front page of newspapers in dozens of countries. It showed things that had never been seen before, not just clearer versions of things Hubble had seen, actually new things, structure in the early universe that existing models had not fully predicted, evidence of galaxy formation processes that are still being worked out, a window into a time so far in the past that the universe looked genuinely different from the one we live in now. And every time someone looks at those images, every time a scientist downloads a data file from Webb and finds something unexpected inside it, they are looking at the product not just of the engineering work that built the telescope and the science work that designed the instruments and planned the observations, but also of the long, frustrating, sometimes painfully honest work that happened in the years before the launch. The work of asking hard questions when it would have been easier not to. The work of sitting with uncertainty instead of papering over it. The work of earning confidence instead of just claiming it. That is the story that tends to get lost, because launches are dramatic and images are beautiful and discoveries make headlines. But the decisions made in conference rooms over 4 years of delay, the decision to keep asking whether the risk assessment was honest, the decision to keep finding ways to improve margin even when the schedule was already bleeding, the decision to bring in outside reviewers and actually listen to what they said, those decisions are part of what put Webb in space and kept it functioning when it got there. The James Webb Space Telescope is the most ambitious scientific instrument humanity has ever built and launched. It is operating at a distance from Earth that puts it permanently beyond the reach of human hands. It is looking backward in time toward the edge of what is observable, toward the moment when the first stars ignited in the darkness of the early universe. It is telling us things about the cosmos that we genuinely did not know before. And it works. It works because thousands of people across multiple continents and multiple decades did extraordinary things to make it work. It works because of physics and mathematics and materials science and precision engineering and computer simulation and careful hands and brilliant minds. But it also works, at least in part, because some of those brilliant minds had the courage to stop and look honestly at what they did not know. 4 years before launch, with a finished telescope sitting in a warehouse and the world running out of patience, the people responsible for this machine kept asking whether they had actually done enough to deserve the confidence they were expressing. And then they did the work to earn it. That is a harder thing to celebrate than a beautiful image of a distant galaxy. But it might be just as important.